I don't know why. Okay. Okay. Orthogonality. By Cauchy-Schwarz inequality, we know that the absolute value of the inner product of x and y is less than or equal the norm of x dot norm of y. So we can say that we have these inequalities. I remind you that if the norm of the absolute value of a is less than or equal b, so we can say that a is between minus b and plus b. So because the absolute value of x and y is less than the norm of x dot the norm of y, so the inner product of x and y is between when we divide this by norm of x dot norm of y is less than 1. So this quotient must be between minus 1 and plus 1. And we can define a cosinus, a theta, as a cosinus inverse 1 of this quotient. So if two vectors be orthogonal to themselves, the angle between these two vectors is p over 2. And we know that the cosinus of this cosinus of cosinus of p over 2 is 0. equals 0. So by this fact from the plan, we define orthogonality. We say that two vectors are orthogonal to themselves if the inner product of these two vectors equals 0. Okay, so we define the orthogonal vectors. Let X be an inner product space for two vectors X and Y. We say that they are orthogonal if the inner products of them equals 0. Another definition, let X be an inner product space. For the set E1 until Ek as a subset of X, we said that this set is orthonormal. Orthonormal. It's a little different from orthogonal. When we say that they are orthogonal, it means that the inner products of them is 0. But orthonormal means that the norm of En must be 1, and also they are orthogonal. So the norm of En for all n from 1 to k must be 1, and En for different m and n must be 0. So when we say that this set is orthonormal, it means that the different vectors of this set must be orthogonal, and the norm of any of these any of the element of this set must be 1. So we have two definitions: orthogonal and orthonormal. Okay. Now we have this lemma. An orthonormal set E1 to Ek is in any inner product space X is linearly independent. Linearly independent. So the set, any set of inner product space that is orthonormal, they must be independent. In particular, if X is k-dimensional, so the dimension of X is k, there is a basis like E1 for a basis like E1 to Ak for X and any vector X we have this equation. Of course, if E1 to Ek be a basis, there are lambda 1 for E1, E1 to Ek as a basis. Just basis, not orthonormal. Just basis in any vector space. So we can write X as a sigma of lambda n En for a scalar lambda n. En. There are unit lambda n's depend on x, so that we can write x as this sigma n from 1 to k. But if this is an orthonormal basis, the lambda n equals the inner product of x and En. So here we must find lambda n, and it can be difficult to find lambda n for x, but here lambda n can be found very easily. Lambda n equals x and En. For orthonormal basis. X and En. So this is a very important lemma that shows the importance of orthonormal basis. Here, as you see, in this case, E1 Ek is usually called an orthonormal basis. Orthonormal basis, and these numbers are called components of X with respect to this basis. Let V1 Vk be a linear independent subset of an inner product X, and let S be the span of V1 Vk. Then there is an orthonormal basis E1 Ek for S. Okay, everything is okay. Voice and the picture is okay. Okay. So the part A of this lemma says that for any x in called the dimensional vector space, that is an inner product space, if this set is a orthonormal basis, this is linearly independent, and we can write any vector x as this sigma such that the lambda n of this sigma equals the inner product of x and En. and we call this basis orthonormal basis, and x and en, they are components of x respect to these bases. The part B says that if we have any basis, any arbitrary basis like v1 to vk, that any basis you know must be linearly independent. So if v1, vk be a linearly independent subset of an inner product space, and S equals the SP of v1 vk, means S is a sub vector space that v1 vk is a basis for S. We can define an orthonormal basis for S. It means that we can find for any basis or for any linearly independent that are maybe not orthogonal, but we can find an orthonormal basis. The proof is a little complicated and difficult, so I leave it as especially B. The part B is a little difficult. This process to prove the B is called Gram-Schmidt algorithm. Gram-Schmidt algorithm. So we should follow this algorithm to find an orthonormal basis from a basis. Vk, v1, v2, vk is a basis, but they are not orthogonal or orthonormal in general. But we can find an orthonormal basis by a process called Gram-Schmidt algorithm. Theorem. Let X be a k-dimensional linear product space. So X is k-dimensional. And E1, Ek be an orthonormal basis for X. So for any number alpha n in F, means any scalar alpha n, we have this equation. The norm of sigma alpha n en power 2 equals the sigma of the absolute value of alpha n power 2, because the norm of en equals 0, so the norm of the sigma power 2 equals the norm of just the absolute, the sigma of just the absolute value of alpha n power 2. The proof is like this. I remind that for any x, the norm of x in a linear inner product space when the norm induced by inner product, we know that the norm of x power 2 equals the inner product of x and y by itself, x and x. X and x. And here the method of proof is based on this equation. The norm of this vector power 2 equals the inner product of this vector to itself. But the first sigma is the index of the first sigma is n, and the index of the second sigma is n. So we have two sigmas, one from n to k and the other from n to k. And because the first variable, when alpha n comes out of the inner product, it will be alpha n, but for second variable, alpha n comes out of the product with bar. So we have this inequality. And we know that if n and n be different, we have En and En, En. The inner product of En and En equals, because this is orthonormal, equal 0 when n is different from n, n not equals n. And it will be 1 when n equals n. So these two sigmas will be this sigma when n and m are the same, and the other cases will be 0. And in this case, alpha n bar equals the absolute value of alpha n power 2. So the proof is very easy, and it will be obtained from this equation, one equation and the other equation. Definition, important definition. An inner product space which is complete, we say that an inner if an inner product space is complete with respect to the metric associated with the norm identity, it means that induced, with the norm induced, but it means that the norm of x equals the inner product of x and x and x over 1 over 2, or the radical of the inner product of x and x. With this norm, if the inner product space is complete, we say this space Hilbert space. So Hilbert space is an inner product space which is complete with respect to the norm induced by the inner product. Okay, I explain this definition here. H with the inner product, we define a norm like this, or like this. So H will be a norm space. Now, by definition, this metric d of x and y equals the norm of x minus y. H and D will be a metric space. Now, if H and D is complete, we call H with the inner product a Hilbert space. So any Hilbert space is a Banach space because the metric induced by the norm or the norm induced by the inner product is complete. So any Hilbert space is a special Banach space. Now some examples. For example, every finite dimensional inner product is a Hilbert space. So if H is an inner product and dimension of H is finite, so H is complete. We know that every norm space with finite dimensional is complete. So that if H with an inner product be finite dimensional, it will be complete, so it is a Hilbert space. So one of the example of Hilbert space is finite dimensional inner product space. Another example, okay, okay, my voice is cut off sometimes. Now it is okay, I think. My voice is okay now? Okay. So maybe it be my voice be disconnected for a while, for a short time. Okay, thank you. Thank you. So I continue. Okay. So as I said, the first example is finite dimensional inner product. Because if the dimension of a normal space is finite, it will be complete. Another example is L2X with capital L, means the space of integrable function that the integral of f power 2 be finite. As you see, for two functions L2x, we define f and g as an integral if g bar be mu. With this inner product, L2x be complete, and so it be a Hilbert space. Another example is L power 2 with a small l, B with capital L, but C with a small l. And this is the space of sequences. Sequences, this is also an inner product, and this is complete respect to the norm induced by inner product. So this is also a Hilbert space. So there are three examples of Hilbert spaces. Okay, the internet is very weak, so we should wait. Okay, now the internet is okay now. Another lemma. Okay. Let H be a Hilbert space. H with an inner product be complete, and so be a Hilbert space. And let H be a linear subspace of H. So Y be a subspace, linear subspace of H. So Y is Hilbert space if and only if Y is complete, and if Y is closed, so Y will be complete. So any linear subspace of a Hilbert space is a Hilbert space if and only if that subspace be closed. The proof is very easy because we know that a subset of a complete space is complete if and only if that subset be closed. Now some exercises. I will send the answer of the exercises, but not all the exercises. The selected exercises I choose some exercises, and I will send the answer of that exercises, and you should learn only the exercises I send to you, not all the exercises. I selected 2 or 3 exercises from each section, so it will be easier to learn these exercises. Orthogonal completeness. Orthogonal completeness. Complements. Orthogonal complements. Complements means if we can write H as the addition of 2 subspace A and B, such that the intersection of A and B is just 0. If the intersection of A and B is just 0, we write H equals A plus B like this, with a circle around the plus. So if H equals A plus B, if A equals A plus B for 2 subspace of H and the intersection of A and B equals 0, we write H equals A plus B with a circle, and we call this plus addition, the addition of 2 subset, as direct addition. Definition: let X be an inner product space and let A be a subset of X. The orthonormal complement of A is the set A orthogonal as the set of all member X of X, such that X and A, the product of X and A, equals 0 for all A in A. So when we say that A orthogonal, this is the set of all vectors, that these vectors are orthogonal to the members of A. Okay? If A equals empty set, we say that the orthogonal of empty set equals x, the space x. So if A equals empty set, A orthogonal equals x. For example, if x equals r power 3 and A equals A1, A2, 0. So A is in the plan of xy because the component z here is 0. Now A orthogonal x, A orthogonal equals the triple 0, 0, x3. And this is the z axis. You know z is orthogonal to the plane xy. Okay. To show that A orthogonal equals the triple 0, 0, x3, we say that by definition, if x equals in general x1, x2, x3, as a member of A orthogonal, this vector will be in A orthogonal if and only if for any A in A, and we know that the members of A are like this, A1, A2, A3. So x and A equals x1, A1 plus x2, A2 plus x3, 0. Because x3, 0 is equal to 0, we just write x1, A1 plus x2, A2, 0. And because we can choose, for example, A1, A2, they are arbitrary. We can choose A1 to be x1 and A2 to be x2. So x1 power 2 plus x2 power 2 must be 0. In this case, when AH equals x1, A1 equals x1 and A2 equals x2. So in this case, x1 and x2 must be 0. So if x as a triple x1, x2, x3 belongs to A orthogonal, x1, x2 must be 0. So just the triple like this can be in A orthogonal. And any members like this will be orthogonal to any member of A like this. So A orthogonal equals the triple 0, 0, x3 for all x in R. I write another example by myself. This is not in the book. If x, for example, equals r power 7 and AB the 7 tuple like this, 0 for x1 it must be 0, x2, x3, and for x4 it must be 0, x5 must be 0, x6 and x7 must be 0. Now A orthogonal is the set of 7 tuple that instead of zeros must be x1, x4, x5, x7, and instead of x2, x3, x4 must be 0. So any member of this 7 tuple that is 0 here must be arbitrary, and every other member that is not 0 here must be 0. Okay? Another example, suppose X is a k-dimensional linear product space and E1, Ek is an orthonormal basis for X. If A equals the span of E1, EP for any P between 1 and less than K, then A orthogonal equals the span of E P plus 1 to E K. For example, if X equals R power 10 and E1 equals 1, the n tuple that the first place is 1 and the other places are 0, E2 the place 2 is 1 and the others equals 0, and etc. Now if A equals the span of E1 to E6, that is all the A like this, the A orthogonal as this example must be the span of after E6. So E7, E8, E9, and E10. And this is equals the members A, that is A equals 0, 0 until the 6th position, and day A7, A9 to A10. Lemma, let X be an inner product space and A subset of X. So we have the following properties. A, 0 is an element of A orthogonal, because 0 is orthogonal to any member. The inner product of X and 0 equals 0 for any X. B, if 0 belongs to A, the intersection of A and A orthogonal equals 0. Because we know that from A that 0 belongs to A orthogonal, and if 0 is also in A, so the intersection of A and A orthogonal is just 0. And otherwise, if 0 is not in A, the intersection must be empty. C. The orthogonal of the singleton 0 means the set that has just one element. 0 equals x, and the orthogonal of x equals the singleton 0. B. If A contains an open ball BAR for an element A and a positive radius R, then A orthogonal equals 0. So if A has contains an orthogonal, it's like this. For example, this is A, and there is a ball like this in A, an open ball. Open ball. If A contains an open ball, the orthogonal of A equals 0. In particular, if is a non-empty open set, because every open because if A is an open set, so every member of A must be inner element, and any inner element, if X is an inner element, there must be an open ball that be in A. So in this case, A orthogonal equals 0. So if A contains an open ball, A orthogonal equals 0. In particular, if A is non-empty open set, in this case, A orthogonal equals 0, 2. If B is a subset of A, the orthogonal of A is a subset of B orthogonal. So the position of A and B as orthogonal changes. F, A orthogonal is a closed linear subspace of X. So A may be not a subspace, just a set, a subset of A. But A orthogonal is linear subspace and is closed. Also, this is closed. And GA is a subset of A orthogonal. Okay, the proof is for your study, and I finished the class, and okay. Here will be our next session. Okay, thank you. Any question? Thank you too. So goodbye.